So hi everyone, I'm Amit. Currently I'm part of a promo recommendation track. So thank you for joining today's reading group presentation. So today me and Sri Balaji will talk about a specific paper that is on multiscale, multiband, DenseNet for audio source separation. So this paper came in 2017, and from the title itself, it suggests that this work actually is connected to different field. One is deep learning, because in the they talk about DenseNet, and another is a specific problem, the audio source separation, that is from a signal process perspective. So in this paper, they mainly actually tried to apply a new sort of or advanced DenseNet architecture to this audio source separation problem, and they showed that their approach or their method is able to do a good separation on the audio. So before going to talk about the paper, the framework, we'll try to give a, first we try to give a, so since me and Balaji said both are presenting, so what we decided that we'll divide the whole framework or whole presentation into different part. So I'll talk about mainly first the problem definition and the basic terminology related to this, and then solution approach in terms of what are the previous methods already attempted to solve this kind of problem, and then what is DenseNet. So these are the part I'll talk about first, and then Sri Balaji will talk about how the progress about how they actually adapted this DenseNet to make a new model, that is DenseNet, that is multiscale, and then they also included a multi-channel. So that's why DenseNet. So these two proposed architecture of the paper, and then again I'll talk about the model performance and the conclusion. So I hope it is clear. Now I'll go to the first the problem definition. So normally this is a common problem in signal processing domain. If you're talking about any signals, it can be considered as a mixture of different sounds together. So let's say for this example, if you talk about a specific source problem from a music background, then you can think about that. Okay, music can be combination, or like song. The music in a combination of different instrument, and here you can see there are 4 different instruments are shown, or 3 different instruments are shown, and when you actually you're obtaining the final output, that is a mixed of those instruments, that is a mixed signal, and we need to identify which individual instrument actually are working or playing in the background. So this is sort of a non-linear, or it is sort of a complex problem to solve, because the mixture of this kind of music itself is a non-linear relations, and therefore it may not be possible to directly separate out all the sources. So though it is looks like it's a simple problem, but solution process may not be that easy to define. So where this can be used, so there are several implementation or the application of this kind of source separation. So you can think about when you're going to make a online AMT model, automatic music transcription, there actually you need to reduce the noise or whatever the background, the noise, that for that it can be used. Similarly, when you're talking about let's say we might want to isolate a singer from a background, right, to make a karaoke. So for that, you can easily use this kind of algorithm to separate out the music, the background music and the vocal of a singer, right? So that basically lyric and music instrument detection, also lyric recognition. So there are several different applications of this. And in mathematically, this problem, source separation problem, can be written in terms of a equation that you can say that, okay, the final output, that mixed signal y, can recognize some over of different x time series, and that actually not coming from different sources, right? So so the idea is that, okay, given a yt, you need to design a model by which you can actually separate out those x, individual x. So this is the way people actually define this mathematically, this problem, and then try to model some algorithm by which it can be possible. So let's say we're just going to show this 30-second video, so you can see.
公立小中学校の教員勤務実態調査速報値によると、 平日の学内勤務時間は、
タンパク質の詳しい働き方を努めたと発表した。細胞の中でタンパク質の品質管理をする組織、状況体の中で働いている。
Sorry, so we like actually don't know the language, but at least we just try to show that, like in the previous example, we're talking about separation of the music sources, but here actually you can do the same thing for audio sources, let's say for different people, right? So here it is the mix of different vocals, and the model actually separate out those individual vocals individually. So when it's running, you can see that like in the starting, it's actually mixing of all the vocals, but then if you apply some model or algorithms by which actually you can separate out the individual vocal. So this is the way you can talk about the audio source of separation. So I'll talk about some basic terminology which normally should be required to understand the paper in the later stage. So when you're talking about this kind of sound representation, we're talking in terms of the time series representation or the frequency series representation, right? So whenever you're talking about some specific source, that source can be represented as an audio, and that audio is nothing but the time frequency representation. So whenever we're representing an audio in terms of time domain or frequency domain, actually you can represent those in terms of some time frequency map. And here actually showed there are 4 different kind of time frequency map. So this is STFT, is basically the short-term Fourier transform. So this is the simple one where actually you are using first Fourier transform to represent your data. So whenever you have time series audio signal, you can do a fast Fourier transform to that, and you can get a time frequency map of that. Similarly, this is the male spectrogram, which normally people use for as input of your model. So this male spectrogram actually similar to the STFT, but the difference is that it actually mapped over a logarithms, and as well as there are certain frequencies which are actually basically discarded from the set. So after given a threshold on frequency range, you can actually remove some of the frequency, and then you can represent it in terms of the logarithm scale. CQT is actually is all like is a constant Q transform kind of this is also time frequency map, but this is 2D representation in the logarithm scale of a center frequency of a time series. And the fourth one is the chromogram. This also similar to one kind of CQT, but it actually plot the energy distribution corresponding to a given set of pitch. So whenever you have audio, you can actually calculate what is the loudness of that audio, and based on that you can find out what is the energy map of that. So these are the different kind of time frequency map representation of a given audio, and these are actually can be used as a input data set for your model. So this is required to understand that. Now let's say you have some model which actually do this separation. So then how are you going to measure that either your model actually able to separate out that audio signals in a good accuracy? So therefore that there are different measures used. For now in this paper they talk about a measure that is called source of distortion ratio, and this one is actually on an average. This is the SDR is actually used generate or like used to compare how accurate your model is. So how it can be defined. So normally when you're talking about a specific source, you actually can define your estimate source in terms of the true source. So and some noise part, right? So this error term actually is coming from different kind of noise. So you can think about noise in terms of artifacts, or some actual noise, background noise, or some interference. So you can say these are the 3 different individual error component coming from different noise representation, and that's why your estimated source and the source target has a difference. And when you're talking about the ratio of this source target and the error term, then actually it's actually defined as SDR. So if your error is very small, then obviously your SDR should be higher, so higher in decimal. So this is the way you can define the SDR. Apart from that, the signal to noise ratio is also another measure which is important, but it may not be in the context of audio separation. But when you're talking about, let's say, some noisy signal, and you want to measure what is the strength of the signal, then basically you can calculate signal to noise ratio. And if your signal to noise is higher, that means your strength of the signal is high. So these are the two important measurement which people normally use in the context of source separation and yeah. So now I think this two term is important because this frequency time frequency representation used as input, and these measures are actually used to see how the model's accuracy. Now, what are the previous methods people already tried? So there are several methods people have tried, but here actually we just shown two different examples. One is non-negative matrix factorization. So here actually this is the example of a non-negative matrix factorization for the source separation for a multi-channel case. So let's say for individual source, you know what kind of spectrogram you have, the time frequency map, and then you can easily decompose that based on non-negative matrix, and that decomposition can be shown in terms of the W and H, and that actually is defined in terms of, let's say, W or H are actually some contain some element, but it actually shows in terms of some specific set of bases. So that means that whenever you have a different sources, you can actually represent those spectrogram based on some representation, vector representation or basis representation, and then actually you are going to talk about how you're going to solve the problem in the reverse way. So ideally, this is the odd mixture signal. So you know the mixture X. So the problem is itself is that the estimate individual WH and the mixing system A from the given X. So you have a given X, and from that you need to identify what should be your estimated A and estimated W and H. So in that paper, they use this non-negative matrix factorization representation to get a prior information about the sources, and then they actually talk about Bayesian representation of those kind of mixture model, and from there how to estimate individual A, W, and H. So once you have estimated W and H, then you can multiply them and you can get back the spectrum representation. From there you can possible to estimate what kind of source it is. So this is sort of like probabilistic approach, but the underlying assumption is that like every spectral representation has individual or independent basis representation, which can actually help to reconstruct those spectrum again. So this is one approach we using non-negative matrix factorization. Before this paper, people also tried some like neural network model. So this is an example of a single channel neural network model, but this is a mixture of a short-term Fourier transform, and from there, if you use your model, it actually basically separate out your source spectra and as well as your task time frequency mask. So once you actually able to do that, then basically you can identify what is the target STF. So this is the way people actually solved earlier, and now in this paper they're talking about some advanced model of DenseNet. So we're going to talk about what is DenseNet. So first of all, this is the way it is evolved. So when you're talking about DenseNet, we should also talk about first CNN and then ResNet and then DenseNet, because that's the way it's evolved. So if I just talk about what is the difference between CNN, ResNet, and DenseNet, so then that is just a representational change of the feature vectors. So when you're talking about the CNN, then it is with one sort of non-linear representation of your given input data X in terms of fx, and that's why it is written this way. Whenever you're talking about DenseNet, you're actually connecting your features not only with fx, but you're also adding that as a new features into the next layer. So that's why it's differently written in terms of the fx plus x. But when you're talking about DenseNet, then that time basically you are actually not adding these features with the next one, but what you're doing basically you are concatenating the features from the previous layer. So that's why it is written fx and x. So so it has an impact because DenseNet actually, the idea is similar to ResNet. You can see that because this is also sort of non-linear transformation, but it is also non-linear transformation in terms of the concatenating, right? But the point is that here actually you are concatenating the identity connection, and that actually help you to make the connection between all your final output layer also. So in that way, it actually helps to move away from like to learn more about your features, and it actually provides a reuse of, like, since in your concatenating in every layer the previous layers features, so that's why it's actually reuse the feature information to learn more about that. So whenever you have a complicated features, that can be easily learned from this kind of representation. So that's why people talk about more dense layer. But the problem is that, like, if you are going to make a dense net, then probably you need a very, because this representation is very memory intensive, so you need a very large memory to train this kind of model. So so I think that is the representational difference. Now from this onwards, in this paper they talk about how they are using a new or advanced version of the DenseNet in terms of multi-scale, and then they talk about another representation that is called multi-channel. So they are incorporating the multi-scale representation from DenseNet representation, and then they're adding from multi-scale to multi-channel. So that's why this is the way it is evolved. So from now onwards, Sri Balaji will continue on the discussion on the DenseNet and DenseNet. Is it any question? Yeah, I think no. Then Sri Balaji, you can continue.
Okay. As Amit said previously, the authors take the DenseNet as the reference model and add a few of the blocks to perform audio separation. Because as we seen previously in the time frequency graph, performing convolution on the frequency axis provides better results on audio domain. Say we have speech recognition and other audio source operations. It performs better when we perform convolution on the frequency axis. So as we saw previously, even DenseNet is taken from the upgraded version of CNN, ResNet, and DenseNet. So in the current architecture, we have two major update. One is, as Amit said, one is multiscale and another is multiband. So as a first step, we are taking multiscale where the input is given to the continuous state of dense block called as by performing downsampling. So by doing downsampling, the input is converted into lower resolution by keep on iterating of the dense block and downsampling. As you can see in the picture, it is provided to the dense block of various sizes. So various sizes in the sense each dense blocks will perform will be operating at various scale. That's why we have different scale size. For this diagram, the scale size is 3, s equal to 3. So to represent the changes, the author has used different sizes for each dense block. We can see there are 3 different sizes in the figure. And similarly, after performing downsampling, the converter lower resolution is recovered to the higher resolution using upsampling and concurrent dense blocks. So why the author is saying that doing downsampling and converting into lower frequency is better in the sense only in the lower resolution we can extract the context very well when compared to higher resolution. So most of the data can be extracted well. The long context or fine grained structure patterns in the audio can be extracted well in the lower resolution. So in the DenseNet, we are performing 2 major steps, that is downsampling and upsampling. So next slide. So if you see what is present in each dense block, each dense blocks has multiple composite layers. When we say composite layer, it performs a composite function. So mathematically, we can say composite function is a function of a function. So let's say here we have an example. Excel is it's an input and it performs a specific operation, say h of x. where we can say the function can be batch normalization, standardization, ReLU, or whatever the function may be. So for the each input, it, it takes the output from the previous layer. So that's why we represent it as L-1. So this is what generally all the basic feed-forward network do in the neural network. So coming to the next upgrade, we use DenseNet, which add input mapping from the previous input plus XL-1. So by doing this, we can provide the gradient directly to the current layer. So it enables the model to learn much more faster than the normal general deep learning architecture. So in the DenseNet, so what they have done is, instead of taking only the previous output from the previous layer, they have taken the all outputs from the preceding layer. From the diagram, you can see for each composite layer, the input is from the previous layer and all the concatenation of all the outputs from the previous layer. So that's why we have it's L of XL-1, L-2 up to the first layer. So this way, as I said earlier, it provides a gradient directly to the current layer. So this will enables the architecture to train faster. So as well as the one more advantage of this advantage is is to get the feature directly from the previous layer, which is already explained by the Amit. So we can extract the features directly from the previous layer, which is very much important to reduce the parameter. So at the end, we are going to see this model is going to more parameter efficient than previous model that is used for a computation. So next slide. So after doing scaling, we are the author is going to next level of upgrade called multi-band multiscale DenseNet. So in audio signal, when we see there are different patterns occurring in different frequency bands. So let's say, as Amit said, we have flute, piano, guitar, and each instrument may operate at different frequency, or each voice of the person may be in different frequency. So we have to apply this M DenseNet architecture in each frequency of the entire frequency spectrum. So what we are doing is, we are taking the entire frequency spectrum and dividing the spectrum into small chunks of data, and applying the M DenseNet multiscale DenseNet on each band. So overall, in the DenseNet, we have dedicated dense blocks for each frequency bands in the audio signal. So we can say that it may hinder the ability of the model to capture the entire audio signal, but finally what we are doing is, we are concatenating all the outputs and providing it to the final dense block to get individual audio signals. So if you see, as I said earlier, lower frequency bands have higher energy, and most of the patterns and data will be available in the lower frequency bands, and they sustain longer than the higher frequency bands, because higher frequency bands have less energy and there will be a lot of noise in higher frequency bands. So this architecture will enable us to differentiate each frequency and extract patterns from each frequency band from the entire frequency spectrum. Next slide. So in the overall, we can say M DenseNet is taken from the DenseNet, and we are doing two major things: upscaling and downscaling to convert the input into lower resolution, and again recovering it to higher resolution. So in the resolution, in the sense, we can say higher resolution in the sense, we can say it's 24-bit.